Socratic Math Tutor here. Today we're going to show that this set here is a circle with radius root 3 and center 2, 0 in the Argand plane. And we're going to do it by three methods. The first method is the simplest, but it also takes the longest. And this just involves letting z equal x plus iy and doing a lot of algebra. So let's start with that. So let's call this constraint something. We might as well call it p of z. And so the problem we're trying to solve is p of z is equivalent to, and I'll just write this out, and I'm also going to square both sides because basically the formula for the modulus squared of a complex number is just a little bit simpler than the formula for the modulus. So p of z is equivalent to this formula here. Let's put z equals x plus iy in. On the next line, we'll get all the real parts together and all the imaginary parts together. Okay, and the modulus squared of a complex number is the real part squared plus the imaginary part squared. So we'll use that formula there, and we'll also use it over here on the other side. Let's get everything onto one side of the equation, and we'll group all the terms involving only x together inside a pair of square brackets. We'll do the same thing for the y terms. Now in this pair of brackets, I'm going to expand everything out and then collect like terms. And in this bracket, we'll just simplify. Let's divide through by 2 to make the numbers a bit smaller. Okay, now a lot of students take multiple steps in completing the square on something like this, but it's really not necessary. So what you should do instead is you need to memorize that ax squared plus bx plus c has a turning point at negative b over 2a, comma, negative the discriminant over 4a. And so what that tells you is that ax squared plus bx plus c equals a times x minus this number, all squared, plus this number. And so really this is our completing the square formula. We'll just simplify a little bit. Cancel that double negative, and there it is. So this is the formula you want to use to complete the square, and that just does it in one step. So let's apply it down here. A is 1. Then we do x plus b over 2a, so negative 4 over 2. We square that, and then we just get this tail bit off the end, which is minus delta over 4a. So minus b squared minus 4ac over 4 times a. And that's just for this first bracket, so we still need the plus y squared here. And now I'm just going to move this constant term over to the right-hand side. And since 12 over 4 is just 3, I'll just put that straight in. Okay, so if you know the equation of a circle, you'll know that this is a circle centered at 2, 0 with radius the square root of this number. And that's exactly what we wanted. So we wanted a circle with radius square root of 3 and centered 2, 0. Okay, now because this was originally a complex numbers problem, I think it's better to remove x and y from our final answer, and just to answer in terms of the complex variable z that we started with. So what we do is we just start off by noticing, okay, and I'm running out of space, so I'm going to go up here. We just start off by noticing that this expression here is the modulus squared of the complex number with real part x minus 2 and imaginary part iy. So on the next line, we can get the x plus iy together. And of course, we started off by letting z equal x plus iy. So we just put that in here. And this is a pretty good answer. If you want, you can go one more step and just take the square root of both sides. So now it's very clear that this condition expresses that the distance between z and 2 is the square root of 3. And so the set of all complex numbers z satisfying this should form a circle with these parameters. Okay, so that was method 1. Let's now look at method 2. And the idea behind method 2 is that we're going to use a formula. So here's the version for just x in the real line. If you want, have a go at just pausing the video and having a quick read of this, and maybe even try and prove this. So if you know how to complete the square, you should be able to do this just fine. There is a little bit of algebra there, it's a little bit fiddly, but if you're good with algebra, you should be able to prove it. We're actually going to use a slightly stronger version, which applies to the complex plane. So up here we have x in R, down here we have z in C, so this is more general, and it turns out that this formula can make quick work of this problem and any similar problems. And what's really nice about this, of course, is that even if these complex numbers turn out to be much more complicated, like even if this -1 and this +1 are much messier numbers, well, we're not going to have to do a whole lot of algebra using these complicated numbers. We can plug the numbers into the formula and we can get an answer out pretty quickly. So let's see how it works. Okay, so once again, we'll go ahead and call this P of Z. And so P of Z is equivalent to, now I'm going to square both sides, and I'm also going to put everything on the left-hand side of the equal sign. So when we do that, we get this expression. And you'll notice that the left-hand side here kind of looks like the left-hand side of our formula. And we can go even further just to make it look exactly like the formula. So I'll leave this bit as it is. We'll rethink this minus as a plus, so plus -1 times this next bit. And instead of z plus 1, because we want z minus beta, I'm going to write z minus -1. And so we can use this formula with a equals 3, b equals -1, alpha equals 1, and beta equals -1. Okay, and we have to compute gamma and c to use the formula. So gamma equals a times alpha, so 3 times 1, plus b times beta, so that would be +1, which is obviously 4. And c, according to this, is pretty much the same thing, but we're squaring and we're taking a modulus for the alpha and the beta. So we're doing 3 times the modulus of this squared, which is still 3, -1 times the modulus of this squared, which is -1 this time, and so we get 2 here. So in this way we learn that this expression equals a plus b, so that's 3 plus -1, which is 2. So it's a plus b times z minus this stuff, z minus, now in the numerator we have a gamma, we worked out that was 4. In the denominator here we have a plus b again, we just worked that out, that's 2. We're meant to square it, and then we need to subtract off this bit, and we're going to add c. So this bit involves the modulus of gamma squared. So the modulus of gamma is still just 4. When we square it, we get 16, and we're dividing by a plus b, which is 2. And then we just add c. We worked it out down here, it's 2. So we need to add c at the end. Let's simplify the line. Divide through by 2. And move this -3 over. And that's it. We're basically done at this point. If you want, you can take a square root. And so we get this expression, the same expression that we got last time. But this time we used the formula, and so we didn't have to complete the square or anything like that. And so if you're dealing with really big numbers, I think this formula is a great idea. Depends whether or not you need to show working and how much working is expected. But if not too much is expected, and if the numbers are quite big, this is a really good method. Okay, technique 3 is going to be one of those techniques that a lot of people won't understand, but if you do understand it, it's actually probably easier than the others. So I think this is probably my favorite one of the 3. And what we're going to do is we're going to try and reorganize this equation so that there's only one copy of z mentioned. So right now we have 2 copies of z. We just want 1. So the first line will say that p of z is equivalent to, and I'm going to divide through by z minus 1. So on the left, we're just left with √3. On the right-hand side, we get the modulus of z plus 1 over z minus 1. Let's now apply polynomial long division here. So when we do that, and you may have to take a moment to work it out, but when we do that, we get 1 plus 2 over z minus 1 inside the modulus. So now we get kind of the clever bit, or the tricky bit. And here's how it works. If you think about it, saying that the modulus of a complex number is a particular value is the same as saying that that complex number is an element of the unit circle, denoted S1, scaled by that value. Okay, so the √3 here was the radius, and that's kind of scaling S1. And S1 is basically the one sphere, also known as the unit circle. So this is the set of all z in the complex plane with modulus equal to 1. So now we can just do algebra with this line. So we'll start off by subtracting 1 from both sides. Now we'll go ahead and reciprocate both sides. And now we're kind of stuck because we're reciprocating this circle in the complex plane. It's centered at 1, it has radius √3. And the question is, what curve do we get when we take the image of that circle under the reciprocation function? Well, amazingly, it turns out that the image of a circle under reciprocation is also a circle, and there's even a formula for it. So this is the theorem we're going to use, and it says that 1 over a circle of radius r centered at C can be described in this way. Personally, I find this totally amazing, and I think it really gets to the heart of why solving this equation results in a circle. I mean, this equation doesn't really look like it would define a circle, but once we go through this process, we realize we're reciprocating a circle, and according to this theorem, the result will also be a circle. So let's go ahead and use the formula. Right, equals, now that the coefficient of S1 on the left goes up here, so the root 3 is going to go into this position. Then we subtract the conjugate of the old center. The old center was at -1, and so we need to subtract the conjugate of -1, which is just -1. Then on the bottom, we square r, and we subtract the modulus squared of the old center. So we're going to square r, then we'll subtract the modulus squared of -1. And so basically we're subtracting 1 here. So let's simplify. And then we'll cancel this division by 2 here with this division by 2 here. And now we'll just add 1 to both sides. And so there you have it. The radius of this circle is the square root of 3, and the center is 2, 0. And I think that's my favorite technique out of the 3. It actually explains why this equation defines a circle. So I hope you guys enjoyed the video. Give me a little like if you found this interesting, and I'll see you next time.